Good evening.
Action.
Good evening, Professor Venkateswara sir, Anna City garu.
Good evening, sir. Ramnayana garu, and good evening to chief guest, Professor N.V. Ramana garu.
Oh, sorry, sir. Good evening, sir.
Good evening, Nidhin garu. Good evening to all of you.
Very good evening, sir. Good evening for every one of you.
GL Rao garu namaste andi.
Anchuri garu namaskaram, sir.
Namaste.
Namaskaram, sir. GL Rao garu, Anchuri
Sir,
garu.
GL Rao sir, good evening, sir. Namaste, sir.
Good evening to all of you.
Thank you, sir.
Raman Rao garu ekkada unnaru?
Narmada madam, good evening.
Yeah, good evening, sir.
Ramana, good evening. Patola Ramana, namaste.
Sir, good evening, sir. Ramreddy garu.
Namaste, sir. Good evening, Anna.
Namaste. Namaste, ne?
Namaste, namaste, ne?
Mr.
Good evening, sir. Rameswara garu. Rameswara garu, good
Good
evening.
evening, Suresh. Suresh, good evening. Suresh, unmute చేసుకోండి.
Shankar Savitri ji, namaskar. How are you?
Good evening to everyone,
Sir, good evening.
Sir, Baburao sir ki padabindanalu. Professor Baburao sir ki సాయంకాలపు padabindanalu.
Sir, good evening, sir.
Good evening, sir. Good evening.
Sir, ఇంటికి ఉన్నారా? Baburao sir, namaste.
Good evening, everybody, sir.
Dr. Rameswara sir, traveling. Good evening, sir.
Good evening, good evening.
Traveling from Iski to Tarnaka via Sikinabad or Meenambag? మా రమణరావు సార్ కమ్మట్లేదు. గుడ్ ఈవినింగ్ సార్, చీఫ్ గెస్ట్ సార్. సార్ గుడ్ ఈవినింగ్ సార్.
రాలేదనుకుంటా సార్. వచ్చారా?
I have come, sir. I have joined.
పేరు డిఫరెన్స్ ఉంది. నమస్తే అండి. మీ సేఫ్టీ అని రాసింది మీ పేరుట.
Change చేస్తాం.
We will start, sir. Please mute everybody.
రమణరావు సార్ నమస్తే. once again
Chief guest join అయ్యారు.
డాక్టర్ హనుమంత్ సార్ సాయంకాలం నమస్తే.
నమస్తే నమస్తే.
Jagu Dada, happy birthday.
Namaste, Anna. Namaste, అందరికీ.
దాదా హ్యాపీ బర్త్డే.
Happy birthday, Jagu Dada. Happy birthday.
బాపురే బాపురే డాక్టర్ బాబాసాహెబ్ తిలరి దాదాకి జై.
Anna, thank you, Anna. Thank you, Anna.
దాదా హ్యాపీ బర్త్డే once again to you. మరి సాయంత్రం బర్త్డే సెలబ్రేట్ చేస్తున్నాం. మరి మీ
మంచిది అన్నయ్య.
టికెటింగ్ చేయాల్సిందే.
అదే అన్న.
Dada, good evening, good evening. I am Professor
Anna,
Management.
Anna, hotel staff, namaste.
జాయిన్ అయ్యాడు. ఓకే.
సార్ గుడ్ ఈవినింగ్ సార్. డాక్టర్ సుధీర్ సార్ గుడ్ ఈవినింగ్ సార్.
Sir, can we start?
Sir. Good evening. Thank you. I extend a warm welcome for all of you for the second endowment lecture of late Engineer G. Prabhakar.
ఎవరో వచ్చారు.
Now I request Reddy garu, Chairman IEI Telangana State.
మహేష్ తో మాట్లాడి టీ కూడా అది చూడాలి.
Thank you, Dr. Venkata Subbaiah garu. Today we have garlanded in the morning with the family members of our beloved past president, the late engineer Prabhakar garu. Respected chief guest of the day, Professor N.V. Ramana Rao garu, FIE, Director, National Institute of Technology, Warangal. Engineer Venkata Subbaiah, Honorary Secretary, Telangana State Center. Engineer Srish Kumar Gunda, MIE, son of late Engineer G. Prabhakar garu, and convener of this event. And our council members, Dr. Satyanarayan garu, our past president, GL Rao garu, Dr. ISN Raj garu, Engineer Sam Prasad Reddy garu, Professor Ramana Nayak garu, our past chairman D. Hanmantachari garu, the director of SK, Dr. Rameshwar Rao garu, Dr. Sridhar, son of late Engineer G. Prabhakar garu, Dr. SP Anchuri garu, Engineer Aruna, Subhash Babu garu, Jagadishwar garu, the birthday boy of the day, KVRS Murthy Garu, and all Narmada Madam and Shankar Shivaratri Garu, and all other committee members who are not visible to me, and P. Ramireddy Garu, Professor Dr. Muhammad Mohiddin Garu, S. Suryanarayan Garu, and Srinivas Garu, and other members who are not visible to me on the screen, and all the distinguished participants who are in this virtual Zoom meeting in the honor of our past president, G.L. Rao Garu. I'm sorry, past president, G. Prabhakar Garu. Ladies and gentlemen, good evening to all. Today, I feel it is a great privilege and honor to garland him in the morning and pay tributes along with his family members morning 10 a.m. at our premises, and also to be amidst this August virtual gathering and extend a warm and hearty welcome to the today's chief guest, Dr. N.V. Ramana Rao Garu, and all of you to this second endowment lecture of Engineer G. Prabhakar Garu, our beloved past president. It's a great honor to remember him on his second anniversary and paying our tributes to the late G. Prabhakar Ji. I have pride and honor to say that the late engineer G. Prabhakar Ji has been an inspiration to many and also to me to become a member of this center, active member of this 2 decades back, and carried all along with him all these years till his last breath. And today I stand before you as chairman of this best state center among all state centers of IEI with his blessings and from the abode and encouragement being shared on me from the heavenly abode. Accordingly, the state center is organizing the above endowment lecture every year. This will be the second endowment lecture. I am glad to inform the Telangana State Center of the Institution of Engineers has been regularly organizing 20 endowment lectures every year on the birthdays in honor of the eminent engineers like Engineer V. Subbarao, Engineer M. Tirupati Reddy, Dr. J. Purushottam, Engineer G. Prabhakar, Engineer Koka Krishna Mohan Rao, Engineer G. V. Subbarao, Engineer T. Hanumantarao, Engineer A.P. Ranganatha Swami, Dr. S. Raghavachari, Dr. Narla Tatarao, Engineer Maturi Gopal Rao, Engineer Gurram Kotreddy, Engineer Atturi Venkateshwar Rao, Dr. J. John A. Murray, Dr. N.V.R.L.N. Rao, the engineers L. Venkatakrishna Iyer, K.V. Srinivas Rao and M.L. Swami, Dr. A. Ramakrishna, and Engineer I. Basavaraju, Engineer Gopi Chand, endowment lectures regularly on their birthdays.
మీ వాయిస్ మ్యూట్ అయింది సార్.
Brahman dear, voice mute on.
I take this opportunity to apprise you all about greatness of late Engineer G. Prabhakar, past president IEI, by reading his brief profile. Engineer G. Prabhakar was a multifaceted personality. He was not only visionary, but also an accomplished engineer, a shrewd administrator, an institution builder, and a great teacher. And he will be remembered by people from all walks of life for his passion to study technical issues from the policy lens with rare sensitivity for principles of sustainability and social justice, humility, and honesty characterized his life and his approach towards assessment of public policy, particularly in the area of irrigation and drinking water in the state. He was born on April 15th, 1944 in Warangal, a historical city of erstwhile Hyderabad domain. All through his educational career, he maintained an outstanding scholastic record. Engineer Prabhakar did his engineering from Jawaharlal Technological University and obtained BA degree from Osmania University, Hyderabad. Despite his vast knowledge on various fields, he always considered himself to be a student with a desire to learn more and more. He completed his PG in Business Administration from Indira Gandhi National Open University. Engineer G. Prabhakar started his career in the State Technical Education Department and worked for about 14 years, including 1 year service in Osmania University. On selection by the State Public Service Commission, he joined Irrigation and CAD Department in the year 1978, a deputy executive engineer. He served the department in various capacities and worked for COT in AP Secretariat as officer on special duty. He had the privilege of attending training during August and September 1997 as one of the 6 participants selected by the World Bank at Washington, D.C., USA for the officers of various states of our country. He delivered lectures as a great guest faculty for practicing engineers from private organizations and administrators of various government departments. He was subject matter expert in various courses for engineers at Administrative Staff College of India, the Engineering Staff College of India, Dr. Marri Channa Reddy Human Resource Development Institute, Water and Land Management Training and Research Institute, Valamtari, and many more institutes. His leadership at the Institution of Engineers India is historic and earned special recognition for the then AP State Center chapter among the engineering fraternity and in the Institution of Engineers at national level. He was one of the legendary Telugu engineers who earned special recognition in the history of Institution of Engineers. Engineer Prabhakar was actively associated with the combined Andhra Pradesh State Center of the Institution of Engineers India. Now it is Telangana State Center. For 3.5 decades, he served as Joint Honorary Secretary in 1990 to 94, as Secretary 94-98, and as Chairman 1980 to 2000, and received honors for all his services. And also he served as the President of this great 102 years old Institution of Engineers. Engineer Prabhakar was unique due to his passion for studying and sharing minute details of the subject as an academician, and continued to retain the perspective of a teacher that he was from the initial years in the Polytechnic, continued his teaching passion by being a teacher for various engineering subjects to AMI students. And all through his career as a practicing engineer, administrator, arbitrator, and policy advisor, he was multidisciplinary engineer cutting across mechanical, electrical, civil engineering, hydrology, and ecology. During his tenure as chairman of Institution of Engineers India, AP State Center, 15th Indian Engineering Congress was organized in December 2000 at Hyderabad, which earned laurels to the then IEI AP chapter. It was a memorable event in the annals of the combined AP State of Institution of Engineers India Center, since it also received the Best State Center Award during that 15th Indian Engineering Congress, and in the very first year of instituting the award. He contributed significantly to the Institution of Engineers national body, as well ever since he entered the National Council of the Institution of Engineers in the year 1998. He was member of various committees and also as vice president from 2002 to 2003 of the Institution of Engineers. Late Engineer Prabhakar was also elected as the national president for the session 2010 and 2011 of the Institution of Engineers India. Engineer Prabhakar, president of IEI, was appointed by the Planning Commission, Government of India, as an ex officio member of the steering committee for a higher and technical education to formulate 12th 5-year plan, that is 2012 to 2017. He was the member of Council of AICT and also the member of Executive Committee of National Board of Accreditation, and his contribution to the technical education has been highly appreciated by one and all. He was the member of International Engineering Alliance, an international body for regulating quality standards for engineering education. During the tenure as Director General of Engineering Staff College of India, Prabhakar is made best efforts to further boost the image of Engineering Staff College of India in Hyderabad of national importance. After retirement from Irrigation Department, he served as officer on special duty in Andhra Pradesh Irrigation Development Corporation from 2002 and subsequently was engaged in arbitration from the year 2013. Drinking water for Twin Cities was also a serious concern since 1973, and options of Manjira was debated for years. Finally, in the year 2000, the government of Andhra Pradesh decided to tap Krishna for Hyderabad drinking water, resolving unending and just and wise policy to bring Hyderabad into Krishna Basin water. So he was also instrumental in suggesting remedial measures like Kaulas, Nala, and a few other lift schemes from Pochampadu Reservoir. He will be remembered for his humble life and humanity, earned many friends and admirers. He departed on 10th September 2021, leaving his legacy behind as a template for future engineers and administrators. Today, Telangana State Center arranged late Chief Engineer Prabhakar second endowment lecture. On behalf of the Telangana State Center of IEI and on my own behalf, I once again extend a hearty welcome to the respected chief guest, Professor N.V. Ramana Rao, FIE, Director NIT Warangal, and all of you to this important and the theme that tall building, high-rise buildings and issues and concerns by the eminent Professor N.V. Ramana Rao. Thank you, one and all. Now, may I request Engineer P. Ramireddy Garu to kindly introduce today's chief guest to the audience before the speaker is requested to deliver his talk. Over to P. Ramireddy Garu. Ramireddy Garu. Okay, sorry, there is a miss this thing. Dr. Venkata Subbai Garu, you are requested to kindly introduce the chief guest to the audience, please.
Right. Thank you, sir. Chairman, sir. Professor, so it is for me to introduce our chief guest, Professor N.V. Raman Rao Garu. Professor N.V. Raman Rao earlier worked as a rector and professor of civil engineering at JNTU, Hyderabad, before joining as the director NIT Warangal. He did his BE in civil engineering from Osmania University, MTech from IIT Delhi, PhD and postdoctorate from UK in civil and structural engineering from University of Wales, Swansea, UK. He has held several administrative posts as Registrar JNT University Hyderabad, Kukatpalli, Hyderabad from 30th April 2012 to 21st July 2015. As the principal of JNTU Hyderabad College of Engineering, Kukatpalli, Hyderabad from 30th April 2008 to 24th November 2011. As director, Bureau of Industrial Consultancy Services, JNT University, Hyderabad from 5th September 2003 to 5th May 2006. As coordinator, Entrepreneurship Development Cell, JNT University, Hyderabad from 1st August 2002 to 31st January 2004. He has edited 3 books and published 157 papers in international journals, conferences. He has organized 12 conferences, delivered several PhDs. He has won several awards, prizes, certificates. To name a few, Outstanding Concrete Engineer Award for the year 2012 by AP chapter of the Indian Concrete Institute. Sir Arthur Cotton Memorial Prize by the Institution of Engineers India for the best paper. Journal. Madam, please mute yourself. Rama, madam. Rama, madam, please mute yourself. State Best Teacher Award for the year 2011 by the Government of Andhra Pradesh. Best Designer Award for the year 2004 by Indian Concrete Institute, AP, Hyderabad. He has been awarded the 1998 Commonwealth Fellowship to pursue postdoctoral research at the University of Wales, Swansea, UK. Young Engineer Award for the year 1995 by Government of Andhra Pradesh and Institution of Engineers, India, AP State Center. He has been awarded the 1989 Commonwealth Scholarship to pursue PhD in Structural Engineering at the University of Wales, UK. He has been nominated as the expert committee member constituted by the UGC for grant of autonomous status to various technical institutions. He has been a subject committee member of Telangana State Public Service Commission. He is a member of Telangana State Pollution Control Board, expert committee member of Telangana State Power Generation Corporation. He has been the convener of MSET for more than 6 years of both combined AP and separate Telangana states. He has been a member of Academic Senate, JND University, Hyderabad, past chairman of the Indian Concrete Institute, AP, Hyderabad. Past Secretary of the Indian Concrete Institute, AP, Hyderabad Center, Executive Member of the Indian Institute of Bridge Engineers. He has held membership of several important state-level government committees. Professor Raman Rao Garu has been a member of several AICT inspection committees, Board of Studies Chairman in Civil Engineering, JNTU, Hyderabad, external expert member of ISRO Departmental Promotion Committee, and he has been a member of several high-power committees constituted by Government of AP and Telangana. He has been a member of the committee to frame affiliation guidelines for affiliated engineering colleges by Government of Telangana. On the invitation from the President of Mauritius, he has been a part of high-level discussion on the need to engage the worlds of art, nature, and science in Mauritius. Professor Raman Rao took over as Director NIT Warangal on 23rd October 2017. Professor Raman Rao, Director NIT Warangal.
Thank you. Thank you. Is my screen visible, please?
Yes, sir.
Yes, Ramana.
Okay,
Yes.
thank you very much. At the outset, let me pay my respects and homage to Sri Engineer Late G. Prabhakar. And I'm very happy that Professor Sri IS and Rajgar invited me for this lecture. And I thought that this is a topic which is of great relevance in the present day context. So therefore, I chosen this topic. This is a topic which I did with one of my students, Professor Anchuri, who is also here, I think, attending. It's a part of his PhD thesis that we did. And so this is an issue concerning the whole globe, not only India. And this is my first slide. And in the first slide, you see the Burj Dubai, the fascinating structure. You should visit this structure. You see the way it is constructed. A lot of engineering is involved, and we should know what it is. So not only there, worldwide, you will find a lot of buildings of different shapes, architecture, engineering. So a lot of reasons are there why they are having so much shape. But all these things, very fascinating for an engineer, and something which, we need to really ponder about. And that's what excited me. And then we started working, and then we found many things which are very important connected as far as high-rise buildings. So there is something called as World Council for High-Rise Buildings, CTBUH, Council for Tall Buildings, which actually designates the tall building based on the height. And you see on the top, the height is calculated from the top of the tower, So sometimes the people cheat by actually putting long towers on the top of building. And but that is what it is. And that is the definition that CTBH has given. And there are several tall buildings, and over a period of time, these tall buildings have evolved. And today, some more, even India now is planning to build a lot of tall buildings, not only statues, all of buildings also. I will talk mostly about buildings. These are some more buildings over a period of time, timeline, how they have actually come. And you see the Burj Dubai is almost 1.2 kilometers high. And just you can imagine, as a civil engineer, if you imagine what is 1.2 kilometer length and then height, is really wonderful. These are the top 10 in 2006, and every year this list is changing. So you can find in the website of the Council of Tall Buildings and Urban Habitat, this one, which is very, very important. Now, it is not only the design, the construction aspect also is very, very important, because, normally, if a two-story building takes, let us say, 1 year to complete, or let us say 6 months, then how much a 200-story building takes? Not just exactly 200 into 6 months. You need to actually adopt different technology, and sometimes instead of going from bottom to up, you may have to come from top to bottom. And so there are a lot of technologies involved, and we should be aware. And you also need to see what is the surrounding situation, how is it disturbing the architecture, the skyline, other things that are very, very important. In fact, there are some very fascinating buildings that are actually been there in the whole country, and these are some snapshots to tell you the importance of these buildings. And this is how the Burj Dubai stands in relation to the other buildings in that area. And I had the opportunity to visit, and really it was quite encouraging and challenging to see, such a marvelous structure being constructed in an area which is on a sea coast nearly. There are some other interesting bridges. This is a Bahrain. The Gulf have actually a lot of such buildings. A lot of money is there, and they can. What is interesting in this building is the architect has actually given a gap between these two. So what the engineer thought is, by connecting these two buildings and putting a turbine to this, you're also generating electricity required for the building. And that was a wonderful idea. And two things, it is adding stability to the building, and it is also generating electricity, sustainable things. And W.S. Atkins was a consultant, and this is something which... so Dr. Anchuri has really worked very hard on these things. And when you actually see the cross-section of the building, you can find the Taipei 101 in Taiwan, where I had again the opportunity to visit. The configuration is simply rectangle with small changes in the edges. Then the Petronas Tower is like a circular thing, and then you got Jinmao Tower, which is almost like a pentagon. Then you have International Finance Center, which is again different shapes. So all these buildings are having and then you have Central Plaza, which is very similar to our Central Vista, but it's a tall building. Of course, it's not the Parliament building. And then, so varying cross-section shape with height, even sometimes the cross-section is also varying with the height. Exactly, in the bottom, it is going from square to round. And why do we need to do this? Am I audible, please? I think there is Am I audible?
Audible, sir.
Okay. My slides are visible, no? They are moving.
Yeah.
Because otherwise, it will not be interesting.
You are perfect, sir. Go ahead.
Thank you. So from square to round, and then can force the wind to behave differently. So, when we think of tall building, it is not the earthquake that is any more important, not the gravity load. The wind load is what becomes critical, and especially in coastal areas, the wind is a very important parameter. And most of them are designed in such a way to reduce the wind drag and thing on the surface. So this results in a confused vortices, which is similar effect to using tapering, etc. So you see the edges, especially in these buildings, are made rough and staggered, so that it breaks the wind speed and all that. So very interesting concept. what we call as vortex shedding. So this is another building in UK. It's called the Swiss Reinsurance. The vortex shedding can also be reduced by adding spoilers. In the surface, there are some projections, of the steel rods like that. So this is actually a surface projection. You go close to the building. So what these people have done is they have put mirrors in that. It looks very good, actually. The most well-known form is a spiral scruton stake, which is widely used on circular chimney stacks. So this is very convenient to use this strategy on diagonal structures due to the geometry benefit and the grid fundamentals. So this is going to break the speed of the wind and also reduce the wind load on the structure. Then you have other structural forms. In fact, the USA's tallest building, this 360 degrees twisted Chicago, still it is under construction, not yet handed over. In fact, the architect came up with a shape which was inspired by organic forms. So, as a part of my lecture, I also tell you how these buildings are very close to nature. They try to learn from the nature. And this is the building elevation, and this is what it is. So it is called a twisted degree. Now we have got buildings which can rotate also, and each floor can rotate independently. So then there is no issue of vastu and other things. So a lot of things are actually happening in the building technology. And most of these I told you are being copied or moving from the natures. So this is the Dubai flower. The structural form has been obtained from that. So this is a Greek firm. Petra architects have designed this blossoming Dubai. So for the proposal for the Jamil, this is now completed actually. I had the opportunity to see it. So design is in the form of a blossoming flower. So the designer, actually got inspiration from the nature by developing the form. Why nature? Nature actually teaches us many things. There are issues, there are trees, which have survived several thousands of years in spite of earthquakes, winds, and all cyclones and all that. So nature, we need to learn from nature, and there's a huge research going on in the building sector, and I think Professor Anjuri also is working on it. Of course, he's a consultant, but he tries and does a lot of experiments. So what we need to do is, we need to carry out stress analysis. Today, we are lucky that, we have got sufficient stress analysis tools, finite element tools. We have got software tools which actually try to analyze to the latest deflection, displacements, all the output parameters like bending moment, shear force. You can get to an accuracy of 10%, 1%. So that is the accuracy that you. So we can do a lot of saving in the material, and you see how then you decide. In fact, sometimes you evolve the form. That was what our topic was. So we start with some rectangular form, and then slowly we evolve into a shape where the stress leveling is there. What does it mean, stress leveling? That means every part of the building is almost having the same level of stress. Otherwise, what happens? There is too much wastage of material you are using. Suppose in the lower portion, the stress is more, you can use thicker, but in the higher portion, stress is less, use lesser material. So that's how the tapering things comes up. Of course, functionality will have to keep it. So all these are very, very interesting concepts, that actually gives a lot of structural insight, and it gives insights a spark in the structural engineers. And today I'm happy that, Hyderabad also, we have a lot of engineers who are working in this area. And I understand there is one seminar being organized very soon on high-rise buildings, or it's already over, I don't know. So this is a Dream Tower, again, Korean architect has done. So this is situated at Yangtze, Seoul. It is designed by, I think somebody is writing on the screen. Please ask him to prevent that. Please prevent anybody writing on the screen because it's disturbing the. So this is a concept image of this tower, is a symbolic icon and a landmark of Seoul, which is a city of water. Cylinder type structures were designed as more economic structure to the wind pressure. So everything is, connected with wind, and the shapes, is something very, very inspiring. Then again, the Dubai Tower I told you, which is actually 1.2 kilometer high, has, almost the main portion is 800 meter high, and the tower portion is there. And there are 1,000 shops, 16,000 parking spaces, and so much space is created. And you have some very fascinating buildings in the country. So wherever there is a shortage of land, wherever there is actually a shortage of space, engineers are coming out with interesting things. Of course, the basic mechanics remains the same. Like the cantilever has to be supported and all that. There's a balancing and all that. So that doesn't change. But they are playing with it, and very interesting things have happened in the building line. So this is another interesting building. I don't know the location, but I think I can find out. And then, these are, when people are fighting for light, space and all that, so these are other things that actually come out. Sometimes you need to have refugee floors, when there's a fire accident, people need to come to a common area. So all these things, a lot of planning requires. And these are all, I just told you that there's challenges that each one has got a separate balcony, play. So, when the clients come out with requirements, the architects comes out with solutions and the engineer has to design it. So these are some of the challenges that people are facing and they are actually solving it. It's not that, no. So this is another interesting building where, you have lighting. It looks like a wave form, but all this wave is given to reduce the wind load and increase the stiffness, which is very, very interesting. This is another building, a bank actually, where the top floors are for parking and then they have done it. So, the concepts are like a simple tree. This is like a tree that you have got a tree trunk and then the branching out. And this is how they have done it. Very interesting concepts and very interesting thing. And this is again one more interesting build. So, the artist was inspired by a idol, some movie. So he said, why not design a building like this? And this is in some Italy coast. So when you have opportunity, please do visit these things because they throw a lot of light. And I think these are another interesting buildings, where people are actually playing with the architecture and these are not animated, they're all real buildings, okay? And very interesting concepts, they come out. Mostly these are our very rich owners, casinos and all these things will be there, shopping malls will be there. So here the client is able to afford a lot of money and get with the, and today we have technology, we have software, we can predict the behavior of these structures under wind load, earthquake load, so combination of loads. And very interesting results are coming out. In fact, this is another building there. The twisting is coming to increase the stiffness, and this is how it looks like. And then we have this is another floor in Malaysia. Actually, you can see this. This is Lisbon, sorry, in Portugal, and this actually is again a casinos. And this is for multiple parking. When you go to such a company, you need to have these sort of arrangements. Then these are multiple buildings, So you see the interesting concept is a bundle actually. It's like a bundle, single, like, in childhood we used to study, that single stick will break, but a bundle of stick cannot break. So they are the bundling concepts. I'll also tell you the structural concepts behind it because these are issues. These some things, interesting things that have come out. And some people actually having a top, with the top itself a city-like of thing, a swimming pool, parks and all this. These are all now happening, especially in Dubai, Malaysia, and you can see hotels, the Skyway. So basically what is happening is, people, so I can build anything, but, the cost is a consideration, the time is a consideration. Today, we've got 3D printing, the shape is no more a consideration. So today, structural optimization plays a very key role, enabling us to create buildings with unique shapes and aesthetics, values, doing more with less is the need of the time, That means you have to do more with less amount of materials, less amount of money, and less amount of time. These are the challenges. So structures by their own nature are sustainable. So good structuring emphasizes on achieving great efficiency and minimization of the material. In fact, I told you that nature is what teaching many of us, and so I call this a nature-inspired building or getting from nature, because we are all loving nature, and you all as engineers, we think about nature more than ourselves. So this is, the skyscraper in Taipei, in fact, was inspired by the bamboo plant, where, you have stiffeners in the middle and very interesting concept. Similarly, the Beijing National Stadium was, it's also called as a bird's nest, was inspired by the bird's nest. Again, this is a very stable arrangement. Of course, it's not regular. It's a irregular arrangement like tying down, but it's very stiff. And this stadium is an interesting concept. Again, when I visited China, I had the opportunity to visit it in Beijing. You should really see these structures. They are very inspiring, and the engineers and architects get inspiration from nature, and you can just see this. And this is, the Lotus Temple in New Delhi. Again, is simply, so, I'm just quoting internationally. We also have wonderful architecture and buildings. So this is called inspired from the Lotus. Okay, this is how it looks like. Then we have the Center for Disease Control in Taiwan. In fact, I had stayed almost in Taiwan for 2-3 weeks as a part of delegation from NIT Warangal and Association of Indian University. So there, these structures, are very interesting, and this is like a research laboratory, and they can see they want to inspire the mind. They want to think out of the box solution. Again, let me tell you, we admit here, even in India we can do it, but here the time cost is very important. The time is important. If somebody is given freedom, that there's no limit on the cost, there's no limit on the time, there's no limit on the space, then we can also come out. So this particular design was inspired by the shell, the sea shell. And the Palm Island, of course, is from the Dubai, be very common, and most of you are aware of it. Then the skyscape in London, which I showed you, the surfaces with all those things, came from this particular plant. I don't know what they call it in English, but then the Olympic Pavilion in Barcelona is a model of the ship, the fish. Similarly, we also have the Chicago Spire. Again, it has been inspired by the shell near the sea. So they go to there and they come out with it. Why not have? So this is a small scale. Why not mimic to large scale? And please note that they are very much structurally efficient. They use optimum amount of material. They use wonderful amount of speed, and the construction also is very fast. And really, they are very inspiring and very good when to see it. A lot of people actually are working in it, and you can just see that. And this is the Abu Dhabi, it's called Al Dhar headquarters building in Abu Dhabi. Again, it's inspired by the seashells. Well, these seashells are so stiff, they can resist the waves impact, and still they are maintaining the shape. So all this, why not mimic it in the nature and see what happens? And the people have done it, and wonderful. But whatever we do, please understand that we will have to satisfy the structural requirements like equilibrium, geometric stability, strength, and rigidity. So as an engineer, if I'm designing a building, I'm responsible for designing a structure with adequate strength, which will not collapse. At the same time, it has got excessive flexibility so that, you can be doing earthquakes, it is safe and all that. So this is just a cartoon sort of thing. Don't take it as a real, but I'm just trying to illustrate the idea that, stability, strength, and rigidity all are important when you actually design. So let us see now, what are the materials that are actually using it, and how these materials really help us to do something. So we have, masonry, timber, steel, and concrete. These are the major material. Now, of course, fiberglass is coming. Glass also is being used as structures. And then, we've got other type of materials that are coming, but they're expensive. So I'll talk only about masonry, timber, steel, and structures. So the shapes which are adopted for the structural elements are affected to a large extent by the nature of the materials from which they are made. In fact, please understand that the relationship between structural form and structural efficiency is very, very important. Form has an important role to play. In fact, my whole PhD was on form optimization, shape optimization, what we call it. So for example, you take a plain paper and put something on it, it just collapses. Same paper, if you fold it and then you release it, so it becomes stiff, and you put something, you can hold it. So that is the idea, and a lot of research has gone, especially in Germany and Japan, where, what they do is they have a paper, they load it, and then they reverse the paper as a structure. So that way, they can come out with different shapes. So the effect is the form is an internal force type, and the concept of improved shapes in cross section and longitudinal profile. So all these things are very, very important. So we should understand the main objective of structural design, however, is the achievement of an appropriate level of efficiency rather than the maximum possible level of efficiency. So this is again very, very important. Now I'll just show you an example how in one of the buildings they have designed to reduce the wind. So this was the original thing. You see, the corner is very stiff. I don't know. Yeah, okay. You just see the corner is like this. So the engineer came up with an idea. Why not make the corner like this? But this has no structural purpose. Of course, only extension of that. So by doing this, 20% reduction in the wind load was there, and because of that, there was 8% reduction in the steel, which came to almost 6,000 tons of steel. So we need to think of ideas when large-scale usage is there, how to optimize it, how to reduce the consumption of steel. And that is where engineering, ingenuity, and all these comes into picture. Again, very interesting. I'm just giving some ideas, how we do it. And then very interesting, they have some openings in the middle. So these openings actually are to reduce the wind load, because you allow the wind to pass So basically now because it's all wind load, the issue that governs is deflection control. Okay, that is a strength anyway we are achieving it, but deflections, people who are sitting on the top floor, they should not feel swinging and they should not feel uncomfortable or uneasy or nauseated. So the codes of practice have been put some limits to the deflection control, but different codes in the different countries have actually come out with different deflection limit. For example, there is some codes in US, you got H by 500, whereas in Dubai you have H by 400. On super tall towers, you got H by 300 because you cannot control the deflection. So what is why deflection control? Because there will be shear moments, if there are openings and then there will be closing of stack joints, and the internal partitions, they break. So that's why the deflection is a very, very important. So what we need to do to reduce the deflection, another challenge, that issue that is. So what Arup is, of course, Arup is a UK-based engineering. He came out with, dampers. So you see in the bottom portion, there is a damper, and this is like a spring. And whenever there is a movement, it actually dampens, and then, so this provides about 10% damping, very high reliability, and this is very useful to reduce the forces in the structure. And there are, of course, some other shapes which are very fascinating for all of us to actually do it and see it. Let us see some more structural forms. So, of course, complex geometry is there in tall buildings. And please note, these geometries are now easily generated through the CAD things and easily created through the 3D printing. And today we have technology, we have software, we have everything. In fact, virtually limitless 3D generative vocabulary with today's software. But just because you can draw it does not mean you should also build it. So there are issues like, fabrication limitations that we need to consider. There are issues of implication on details. There are issues of cost implications that we should be responsible as engineers. Of course, geometry frequently has a major impact on the cost of the buildings. So this is again an interesting building. Why this building was bent like this. You see, actually, if you see the cross section, this is consisting of frames and then steel tubes all around. So again, Italian building, Arup has designed it. And what they did is, they did some, the structural concept was, they provided bracings like this, and then even the Statue of Liberty, if you see, actually is all steel tubes. Even our Statue of Unity, the internal is a concrete frame and all that. So very interesting structural concepts, especially when things are going tall. Should visit and try to think, very interesting. So the bracing, allows for transfer load between columns and provides lateral stability. Similarly, the columns you have on radial to follow the gravity load, and then you have center of mass and center of stiffness close to each other so that the torsional, the twisting moments because of earthquakes are not there. So this is what is really driving the structural concepts. Then we have, I told you in the Middle East, this residential project, and you see the surface, the surface are all sort of stiffness. So what it does, it actually, they are doing this vibration analysis, model analysis, how they twist in different modes, and this is what it is. And then you come out with the best shape possible, and this is the plan of that variation. And based on that, you can arrive at location of stiffness and other things, the deflection control. So a lot of analysis goes, a lot of issues are there, a lot of concerns are there. It's not just, people are building, you design, I build. No. You have to see the structural safety, the structural stability, everything. So that is what driving it. Then we have this another interesting building, which looks like this. It's a L shape in the middle, and then things. So from a structural engineer's point of view, tall building is one that by virtue of its height is affected by lateral forces to an extent that they can play an important role in the structural design. Of course, multi-story design provide a large floor area. Why we are building? Because, they provide a large floor area in a relatively small area of land. So everybody goes for it. You can't stop it. But now what we need to do is we need to make sure that it is designed properly. So I told you the Council of Tall Buildings. In fact, I held one national conference at Hyderabad on this tall buildings design. That's how my interest generated. And I can tell you, even though it was a national conference, we had about 25 international participants who came, including someone from Council of Tall Buildings. And they gave us a lot of ideas. There was a quote that was being written at that time, and a lot of things from the national conference, which was held by me as a convener, was incorporated into that quote. So I feel really proud about it. This is all when I was at JNT, of course. So what the Council of Tall Buildings says is, it defines a tall building as a building whose height creates different conditions in design and construction. So, I'll show you some examples of buildings, how it is different from different things. For example, these two in the world, of course, is now no more existing, but this is the World Trade Tower. If you see built of it, these buildings, of course, we need to design for dead load, the live settlement, thermal, and these are the loads that we need to consider. You cannot ignore. Of course, dead load consists of the other things, and you have the live load is the important parts of the building, just as people and furniture. Settlement, the soil, you have towers like Leaning Tower of Pisa. So we need to consider so much weight is falling on the thing, whether it's going to trigger any earthquake, whether it's settlement, all these things. Then we have thermal loads because of sun temperature changes. Especially many of these buildings are countries where the temperature day to evening temperature variation is very high. Then dynamic, especially like the work or the way like movement, and then we have seismic, the earthquakes, and then the wind load. So that is what actually. So these loads definitely we have to consider while designing the thing. So in tall structures, luckily wind and seismic loads are more predominant than other forces. So we do load combination and we take the worst combination out. And hence the lateral stability is more important. So we are more about lateral stability, not the vertical stability. And that is again what drives us. So these lateral forces are coming because of the wind pressures on the sides of the tall buildings, produce base shear. Brahmareddy garu, how much time I have actually? Brahmareddy garu. Is anybody there at the other end?
Sir, you can continue, sir. It is very interesting, sir.
Okay,
please.
Because I have to maintain time also as a teacher. Okay, sorry. So these forces cause horizontal deflection. So horizontal deflection, the top of buildings will drift. Yes. Yes?
Sir, you can proceed, sir. No problem, sir.
Okay, thank you. So I'll take another half an hour and close it because I know people are old and they might have some other issues. So horizontal deflection on top of a building is called drift. So drift is, I'm telling you this in very simple language. When you go into the course, they are very complex language. But I try to, because when I'm trying to tell, especially these are all called as popular lectures. When these lectures, even if you're not an engineer, you'll appreciate it. That is how the lectures are designed. And the idea is, people should be sensitized the importance. You just cannot do the way you want, especially the politicians, they come out with ideas of higher structures, but we need to take into account all the things and many things. So drift is very important. Drift is measured by drift index. It's called a delta by H, where delta is the horizontal deflection at the top of the building and H is the height of the building. In fact, this is how we call it, the drift definition is. Suppose if this is H is the height, and then this is delta is because of wind load is a lateral shift. So drift index is delta by H. So IS code says, that again, we cannot ignore IS codes. The drift index to be not more than 0.002 of the total height. But if you follow this in high-rise building, you can never design a high-rise building in India. So that's why we go to international codes and we try to escape many of the things. So the lateral forces I told you is that, and then wind load, you have again approaches for solving different. So normally the story heights are of the order of 2.7 to 3 meters. So you have static approaches and dynamic approaches that are actually being applied for analysis. I've not put any equation in my presentation, so please don't get scared. So now, what is the effect? Just imagine the effect of wind load is to cause vibration and swing in the building, like earthquake. Okay, the building itself is strong enough to withstand normal wind loads by swaying. The tallest building sometimes sways several feet, but the sway of the people is very important because it should be enough to make people seasick and cause objects in the buildings to fall over. So therefore, we have to have a control on the drift, and that is what is done. So what people do is, these studies are done in different laboratories. In fact, we have done it at NIT Varangal, IITs also in UK when I was doing my PhD with these studies. You see the wind flow is there in different shapes, and you can study how much intensity is there of the wind, what is the velocity, and you take different shapes and then behavior of different shape with respect to vortex shedding. So this gives us an idea. You're not just doing arbitrary. You are thinking what is a shape that actually reduces the minimum weight. You allow some gaps so that wind passes through that. There's some crossing, all these things. So you have a lot of opportunity to experiment and do this. It's called as water shedding because of crosswind. And you see again the Taiwan Taipei. I was wondering why they put the surface like this. But this surface is to reduce the so rough corners. If you have, it can reduce water shedding effects. And again, the Taipei 101 in Taiwan actually is called Taipei 101. because there are 101 floors. On the top of the floor, you can see the whole of Taiwan. Very wonderful. So the corner modification, by doing just taking a rectangular, you are not doing much. But slightly doing the corner modification like smoothing and other things, roundness and other these combinations, you can really reduce the wind loads in it. In fact, some buildings, they have openings. Why they have openings? Because the slots reduce the wind forces and sway from water shedding. So these openings really, again, help people to reduce the wind load, and very interesting things come out of it. And sometimes you rotate the building and twist, because this rotation will minimize the load from one direction, and also twist avoid simultaneous water shedding along height. So that is the advantage, So when you're changing the shape, as it goes high, the water shedding gets reduced. So that again, so all these shapes are not just done out of curiosity. There's a lot of engineering in it. There's a lot of technology in it. There's a lot of science behind it. And that is what is curiosity. And so, coming to earthquake load, of course, it's not important. But again, that the magnitude of earthquake load depends on the mass of the building, acceleration of ground, nature of structure, seismic coefficient methods, and we have response spectrum method and all these things that are actually there. I mean, these are technologies that we have to learn and use it. But now, softwares are there which can do many of the things you don't have to do manually. And so seismic motion, as we are aware, will cause of horizontal and vertical ground motions. The vertical motion is much smaller in magnitude, and factor of safety provided against gravity loads will accommodate additional forces due to this motion. The horizontal motion of the ground causes most significant effect on the structure by shaking foundation back and forth. You can imagine what happens in an earthquake, okay? We're all engineers, we know what it is. And the mass of the building resists this motion by setting up inertia forces throughout the structure. In fact, the effect of seismic load is more intense vibration than those caused by wind. That causes vibration at many frequencies. So that is again very interesting, If there are many frequencies, if the frequency, natural frequency of the building matches the frequency of the earthquake, then resonance occurs and then collapse occurs. So this may cause building to contort, may also cause building to collapse. So let us see now different mechanisms. How do you actually reduce these forces because of earthquake and wind? So these are what we call as lateral load resisting frame systems. We have 4 types: moment testing, brace frames, shear walls. We have several combinations. We are doing a lot of work on it, but I don't want to discuss that. But simple things I'll tell you. So these concept system, again, you've got shear frames. So what I show you is a framing system. It looks like this. You've got interacting system. I'll also show you structures, real structures, and how they are mapping on it. So interestingly, you see these are the configurations. And again, this has been given by the Council for Tall Building. It's a wonderful organization. Does a lot of research and encourages a lot of innovation. Every year they constitute awards, Innovate Awards, and a lot of new things are coming up. So the moment resisting frames are columns and girder plane frames, which actually you will find that they are fixed or semi-rigid connections. Moment resisting constructions and joints between the columns and beams resist the lateral forces. The moment resisting frames are generally steel structures with bolts or welded joints. Then we have concrete moment resisting frames, steel moment resisting frames, and composite moment resisting frames, which are used actually. So these brace frames are like X braces and K braces. I'll show you some examples now. So they act in the same as shear walls, So you might have wondered why they're putting X and K and all this. These are very important because the vibrations may cause the bracings to elongate or compress, in which case it loosens effectiveness. So therefore, we generally don't use concrete brace frames. You have only steel. So I'll show you. Then you've got X bracing system. This works well for about 20 to 60 story height, but does not give, when you have X, you cannot allow the vehicles to pass below it. So this is now used for openings such as doors and windows. So to provide more flexibility for the placing of windows and doors, K bracing systems or full story knee bracing systems can be used. In fact, knee bracing is efficient in energy dissipation during earthquake loads. Now, this is how X brace in a building. So imagine in a ground story, this is there where the car will enter, they cannot enter. So K is a good idea, or sometimes knee brace is a good idea. So all this is coming, out of intuition, issues, concerns, and then you solve it out. Then you got the shear walls, which is the latest techniques. The shear walls are plain elements up to reinforced concrete thin walls, having length and thickness, providing lateral stiffness. They resist lateral loads. They are very rigid. They receive lateral force from diaphragms, and they have lesser ductility and may not meet the energy required. So what happens? Let us see. So again, this is an example of a shear walls. This is a normal frame and a building. Up to a certain height, you can do it. And these are shear walls. And there's a wall actually, and with some openings. And sometimes, these walls are also braced inside. So these are all lateral load resisting system to reduce the wind load, earthquake load, the stiffness, improve the stiffness. So let us now see the examples of how. So this is a building in Chicago in 1895. So this system, up to 10 to 15 story, we can use it. Beyond that, we cannot use it. Then we have a building, it's called Flatron building, Can you imagine a building of this shape? These are all existing buildings. Please note, these are very old buildings. In 1902, they are built and the concept is, they are actually, you require a wider base at the bottom, and this is very tall, about 87 meters tall, 21 stories. Of course, a lot of engineering goes into it. Then you have building like, the frame tube system that you have, the 3D, you have got frames all around the building and tubes and like that. And these are lateral systems, so which actually are very good, and they provide very stiff movement. Then we have gravity loading, and approximately this type of arrangement can be used from 40 to 100 stories. Now, we started from 10 to 12 stories to 20 stories. Now 40 to 100 stories, we can not more than that. This sort of arrangement. So this is again a building like this. So the World Trade Tower, they had used this type of framing system. Then the brace tube structures. So in addition to the vertical frames, they also have tubes with X bracing all over things. So structures behaves under lateral loads more like a brace frame, reducing bending in the members of the frame. The spacing of the columns can be increased and depth of the girders will be less, thereby allowing large size windows than in conventional frames. So you will see here that this is a building again, Yokohama Tower, 296 meter high, and this is what is done in the outside. Of course, this is a real building, but when you go to the structural system, you find this X bracing. This is a truss bracing with the system, and you actually see this wonderful thing. Then you have a tube in tube. So you have external tubes. A type of frame tube consists of an outer frame tube together with an internal elevator. So internal tube is there or the elevator is there, and a service core. So outer and inner tube act together jointly in assisting both the gravity and lateral loading in a steel frame. So how does it look? Then you have got bundle type, bundle tube with belt truss, taper. So let us see some examples of these. So this is a bundle, the Sears Tower in Chicago, which Faisal Rahman has designed. It's a bundle type. Bundling is more stable. So you imagine, these are built in 1974. Today we are in 2023, and so much change technology has come, but still some of the concepts, civil engineers are going big and big, and electronics are going so small and small. So somewhere, there's a challenge for all of us. So these structural systems bundle, you have different combinations coming out. You can bundle either 2-way or 4-way or all the things, like you have the magic box, you can do it and test it. And these simple experiments can be done in the labs of the colleges, universities, and you can correct. So if you have just do this, you have 50 floors. If you can do like this, about 66 floors, then 90 floors, then 100 floors, you can go on going, till the sky's the limit. Then you have got the bundle system, a system like this. You see how the configuration is changing. Till certain level, you have a rectangular, then this, and finally, on the top, it looks like the Bank of China, Hong Kong. In Hong Kong, this building is there. Please do visit when you have opportunity to visit. And these concepts are really very, efficient, very interesting, and they'll ignite your mind, why this is like that. If you can really enjoy, you can do it, of course. Then you have a structural system, tripod system, like, we have tripods for our cameras and all that. So this concept is providing the stability of the base. This is called Mile High Tower. Again, somewhere in China, it is there. So very interesting concept. Then we have the 21st century Dubai, actually, or Emirates Tower. And these are some 269 meters high. Then you have the Burj Al Arab. This is a hotel, actually. There is a hotel, and on the top, there is a swimming pool. So these concepts, what we learn in the labs, all these are simple mechanics, okay? What we learn, how the force transmission is there. So the idea is to see that the force transfers efficiently, the material is used efficiently, the look is very good, and all these concepts you need to do it. Okay, then you have other towers, just quickly example showing the Chelsea Towers, about 251 meters, and then we have Emirates Hotel Tower. These are hotels, Again, I told you, somebody has to be able to afford this type of things. Otherwise, the governments cannot afford and individuals cannot afford. But yes, somebody like Ambani and Adani can afford. So they can put the money, and we can do the design. And Dubai Tower, actually. Most of these are in Dubai, of course. And then this is Mosque Tower, about 185 meters high. Hotels are there. Then we have Shangri-La Tower, China. Then we have another tower in London. So the design criteria, I told you that this is what is important. The strength is very important. Stresses should be within the permissible limits. For example, steel strength is there, the concrete strength is there. Should be within the permissible limits. You should have a lot of factor of safety. And the serviceability requirements, like the deflections and displacement, should be within the specified limits. Then whoever is staying in that, there should be human comfort, like accelerations within specified limits. Then stability, of course, is very important. Sufficient safety against buckling and P delta effects. And then ductility. Sufficient safety against yielding under extreme events. So, whatever we do, we have the objective that there should be service to satisfy the serviceability requirements, should satisfy the strength requirements, should satisfy the long-term durability requirements, should also satisfy the overall life cycle cost. So, this is the boost the buy. So, any structure that we do, a lot of engineering goes into it. We have to first input the loads correctly, load combinations, then you have to analyze. Today, we are lucky that there are a lot of softwares available which can accurately predict the displacements, the outcomes, to a near accuracy of less than 1%. Then we have to see the responses that like bending moment, shear force, deflection. And then based on that, you can change the shape and do this. You can do it several times because now you are not doing it, a computer is doing it. And you can do mathematical modeling and arrive at the most optimum design, in fact. So optimization is again very, very important in these things. And that is where my student, Sri Anchuri, has worked a lot on it. Of course, I stopped at it, but he's still doing a lot of things. And he himself is now an authority in this area. So design issues are very important. Like an ideal structural system should be one which the steel required to carry the gravity load should also carry the main load. So you don't have to put extra steel. Whatever is sufficient for gravity. So that's where the optimization comes in. So optimization could be such that the wind could be carried out with the keeping stresses within the difference between allowable stress for gravity plus the additional stress. In normally 1/3 we increase the stress when wind load is there. So this 1/3 increase allowed in the allowable stress may be just sufficient to carry the wind. So premium for wind is often minimized by an optimum design of beams and columns and floor systems to match the given stress limits and drifts. In fact, the height to width ratios of building are very, very important. So the efficiency of the structural system is often determined by its height to width ratio. The large width for any height usually means larger stiffness. So this implies larger bay widths and larger lever arms for flange frames in frame tubes. So the optimum height to width ratio should be between 5 and 7. So this is how the different things are there. The span dimensions for girders are there. The beam and other things, the dimensions are very important. You cannot have a 2-meter depth beam. Span length often determine the steel quantity of the flooring. Small spans and small heights will really give efficiency. So smaller spans for exterior frames will lead to a more efficient frame. So what they do is in the outer frame, they place the columns very close, but inside they space it. So that is very. So sometimes in the World Trade Center, the span was up to 1 meter between the columns. But inside you can have 4 meters, 5 meters. This is a very good idea that you can do it. So member sizes also are very important that you need to decide when you are arriving at, since the proportion of members of the frame play a leading role in efficiency, with deeper members being more effective in releasing drift. The larger column widths and deeper spandrel may lead to more efficient frame tubes. The column spacing could be arranged in such a way that all gravity steel can effectively carry wind with very little increase in weight for the girders. So floor also is very important. The floor framing is about 20% of structural weight. It takes almost 20%, very important. So the span to depth ratios, the spacing of the beams, the slab thickness and composite design should be carefully considered in the floor system design for us. The span to depth ratio normally, in the range at 20 to 24, which is what we actually do. So these are the configuration. There are some undesirable one and preferred. Don't do like this, but do like this. For example, you have a situation like this, do it uniform. Instead of heavy top, you do it taper it. Instead of sharp entrance, D-entrance corners, you break it into 2 buildings. So this is what teaches the structural concepts. So how do engineers contract these loads? And there are different ways of actually reducing the loads on tall buildings. So in contrast to the conventional approach, advanced techniques for earthquake resistance is not to strengthen the building, but to reduce earthquake generated force upon it. If you go on strengthening it, then you arrive at a building which is too costly, too expensive, but you have to find ways to reduce the force in it. So the techniques are like base isolation and energy dissipation devices. So you will find like base isolation. The board itself says the base has to be isolated. So only the base will vibrate, but the top will remain stable. So isolated base of a structure is supported by a series of bearing pads which are placed between the building and the building's foundation. So you have lead rubber bearings and other things like what we have in the motorcycles and car. So idea from the automobile things are transferred here. So lead rubber bearing is made up of layers of rubber, like neoprene bearing on a bridge. All these ideas are taken and then you put in the building. So bearing is very stiff and strong in vertical lines. Just see what happens now. So this is how a building is done. So this is a bearing, and you rest the building on this bearing so that when there's earthquake, the movement is like this. So in rubber layer, so that the force is not transmitted to the building on the top, and this will reduce the load. So you have different types of dampers like friction dampers, but a lot of research is in dampers itself is going on. So by equipping a building with these additional devices, which have high damping capacity, we can greatly decrease the seismic energy entering the building and thus decrease the building damage. In fact, dampers, I will show you an example, very similar to a vehicle. So this is the system involved and very easy to construct. And most of so future, you will have buildings which are like this, and it may not, but you can still design it and see that it satisfies the needs of the thing. So this is the imagination. Sky is the limit, and for engineers, with the technology, with the software available, you can do wonderful buildings. So another area which actually in high rise a lot of concern is we call it green high rise. So somebody asked me, what is green high rise? Just painting the building green? No. Just by painting the building, you don't get a green building. You need to think of other things, how ecology and other things are there. So for example, why green? Because Prabhakar was also working in a lot of sustainability issues. So I thought I should also include this in high rise buildings. How do you satisfy the sustainability issues? So this is a green building. You have very little energy use, carbon dioxide emissions, and water usage can reduce up to 40%, and the wastage up to. So if you do that, a lot of projects are coming in the city of Hyderabad, and any of these concepts they apply, I think it will make a lot of difference to change. So these are sustainability issues. A lot of steps are there. So building. Let us come to building. So first, orientation is very important. So orientation is very important to make a skyscraper energy efficient to enjoy the gifts of the nature. So green skies, a global movement of green skies upon us, like architects, engineers, developers, and clients, with the influence of governmental guidelines are pioneering shift. So energy efficient ecology, efficient water recycling, quality indoor air. So these are things, which we need to take it. So globally, drastic change is coming in the city infrastructure, and everybody needs going. So India, today, we are leading G20, and a lot of things are there. So 75% of India's 2050 has been built, yet to be built. So a lot of construction activities are going to happen. A lot of cities are building now. So energy becomes a very critical thing. In fact, our Honorable Prime Minister said, we want to become a world server by 2022. Already we have done. So these are clean energy things that are going to happen. In fact, in the COP meeting, he said by 75 we should have a zero carbon dioxide emission. So all these promises are leading us to thinking of green building, and a lot of competitions are now available. At the top of the building, you're actually putting a lot of these things. And then green building materials are there. But we need to see the structural efficiency, the energy efficiency, water, all these things are very, very important. So, material efficiency, waste reduction, the way you are, all these things need to be considered. Issues need to be considered if we really want to make India a green country and other things. You have now, in Italy, vertical green habitats. So on the buildings, they are building forests actually. So vertically designed natural human habitats called eco skyscrapers. They can protect valuable open space. So there was some issue concerning the birds. Birds cannot fly beyond certain heights. So bird strikes were there, they're killing. So these have been resolved now. So you have to start thinking green, especially the rooftops can all be greens, the gardens, because now there's no space in the bottom. So have the greenery in the top of buildings, on the steps of the building, and you can start seeing green things are going to happen. So this is an auditorium in Taiwan. The roof they have made green. People actually sit on it and talk. And below there is an amphitheater and other things. So green tall buildings. So these are again green buildings where a lot of things are. These are all green. This is in Taipei, Taiwan. Taiwan has been it's a small country, but you see the type of innovations that they are doing is really amazing, and I think it's very inspiring for all of us. And then Rotterdam also these green buildings are there, and then you have vertical farming. So the inside of the tower is devoted to the guiding principle of the Rukun Nagara, introduce skywalk safely, So you build a forest and then buildings inside the building, and then these are some other things that are coming. So, now the concern is regarding the birds. So there is a restriction now coming. The birds can't fly, so they're hitting these buildings. Where there's greenery, they come and sit and they can't move forward afterwards. There is a problem and a lot of things. So there's a limit that has been put by the governments. So you see here, this building height is restricted, so the birds can flow over it. And this is again, most of the buildings are going to be looking like this in the future, because we need greenery, we need green buildings, we need safety. And please note that these are not animated, these are all real pictures done by, and this is how it's going to look, top of building. And it's not on the ground, it is on the sky. And today, structural engineers have challenges that they need to in the Gurgaon. So if you see, go to Gurgaon, you find these green buildings. Very interesting there. So we call star ratings, platinum ratings for the green buildings. The government also now insists we build green buildings. So most of the collectorates in Telangana have been treated as building. And then this is again a green building, because the space between them is used for generating energy, sustainability. So it becomes a green building. Energy efficiency is very, very important. So renewable reduction, the use of fossil fuels can also be added by like solar on the rooftops, and then wind turbines in the gap between building, and reduce their economy. So this is the future, and now I think we need to think of things which will actually make a difference to the students. So thank you very much. I just wanted to raise these issues, and I don't know whether I've taken more time. So I would like to conclude by saying that good preliminary design and optimization leads to better construction, erection costs, and better construction. So start thinking green, especially for high-rise buildings. We want to achieve better health and better environment. So namaste, thank you very much. Thank you, organizers. I'll just stop sharing, and then slowly, if someone wants some questions, we can take. So thank you, sir. Thank you very much. Hello, am I audible?
Yes, sir. Yes, sir.
Yes, sir.
Thank you very much.
Good evening, sir. Wonderful lecture, sir. Congratulations, Dr. Raman.
Thank you.
Raman Rao Garu, very
Sir.
wonderful lecture.
Thank you, sir. No, I just made it for a general audience.
No, very, very interesting lecture.
Thank you, sir.
And you have kept up the status of engineer.
Yeah.
we all feel proud of engineers.
Yes,
Though we are not able to do those things, we are a part of that.
Yes, sir. Thank you
A
very much.
very encouraging lecture for engineers.
Thank you, sir. Thank you very much. Any questions I'll take, sir?
Namaste, Raman. I'm Venkatesham. Your junior.
Namaste, sir. Namaste.
Sir, hats off, sir. అసలు ఏంటి అది ఇప్పుడు చూస్తే కాలేజీలో చదివింది జీరో అనిపిస్తుంది సార్.
సార్ మనం ఒకటి సార్ మేము ఏమనుకుంటే ఇట్స్ లైఫ్ లాంగ్ లెర్నింగ్ ఫర్ ఆల్ ఆఫ్ us we need to learn లైఫ్ లాంగ్ సార్.
అసలు ఈ రోజు టోటల్ గా ఇన్స్టిట్యూట్ లో ఈ రోజు కంప్లీట్ టాపిక్ ఇది సార్, మొత్తం హైరైజ్ బిల్డింగ్. అసలు మాకు ఈ రోజు అంతా మా మూడంతా బిల్డింగ్ల మీద ఉన్నాం మేము. ఇంకా ఇక మళ్ళీ మీ క్లాస్ కూడా ఇంకా అదే అయిపోయింది మళ్ళీ.
అదే ఈ రోజే నా సెమినార్ మీద
సెమినార్ మొత్తం ఇదే. మేమంతా ఆకాశంలో ఉన్నాం సార్. మళ్ళీ మీరు దిగుతుంటే మళ్ళీ మీరు పైకి లేపారు.
సరే దిగండి.
సార్ వెంకటేశ్వర గారు ఈ జాయింట్ స్ట్రక్చర్ సార్, ఎంటెక్ స్ట్రక్చర్స్ ఇన్ ఉస్మానియా ఇంజనీరింగ్ కాలేజ్.
Yeah, I know, sir.
Yeah.
Sir. Thank you, sir. Thank you.
Thank you, sir.
Again, మా గురువు గారు మాకు చూస్తే మా గురువు గారు గుర్తొస్తుంటారు.
Thank you, sir.
Daddy. Thank you, bye, sir.
Thank you, sir.
Sir, if no doubt.
This is Sri, sir. Can I have a couple of minutes, sir? I have a couple of questions.
Yeah.
Yes.
Namaskaram, sir. Nenu Srish Prabhakar garu abbayini. So it was very insightful, sir. First of all, the lecture has been, very, very good. Ippudu mem entante we will start looking at these structures in a different perspective. I mean, what kind of design people must have, thought about, right? So instead of just looking at where and when, but we'll also start looking at the things like, how did they design? What exactly, different things they put in perspective while designing. So very insightful. My question, sir, is you said that we are started putting some bearings and dampers, right?
Yeah.
So do we need to have any kind of maintenance?
Yeah, actually, most of these are supposed to be, maintenance free for a long period. But of course, because these are mechanical devices, they need to have some maintenance. So there is a mechanism. If you go to Burj Dubai, you will feel, there is a special mechanism to maintain, especially the bearings and the neoprene bearings. Maintenance is required definitely. But not regularly, over a period of time, every 10 years or every 5 years, like that. So they put oil.
Okay.
They are mechanical devices, you see, so they need to.
And the second question I have, sir, is, these tall buildings were basically a necessity like in maybe 1950s, 60s or 70s, because we didn't have this kind of internet or network where people can talk to each other and, get the things done. So people have to go personally in person from one location to another location to get their businesses done. But now, because of globalization, everything is in tips of their hands. Do we really need these kind of tall structures?
See, if you see the question, in places like Dubai, where there's a shortage of land, you don't have a choice. Everybody wants to be in the heart of city. So that's how these are, the city is the mother of invention. And there a lot of new buildings and high-rise buildings have come up, and something which I think are really very challenging for engineers. And in India also, you are coming up with wonderful buildings. Because we have statues, today also one statue was inaugurated at Telangana, and then we had the 180-meter height tall statue of Sardar Patel at Gujarat. So these are tall structures, they require a special type of engineering. So need is a necessity, is the mother of innovation. If there's a need, yes, then only people will say. Like hotels, tall building, when somebody is in a top hotel, you actually have a better view of the whole thing. And that is how, in fact, I don't know how many of you have visited Macau. If you go to Macau, from the towers, you can see the China. So those towers are called, and there are a lot of tourist attraction. And over a period of time, they'll recover the cost also. So these are, you can say, for multi-purpose. So whether requirement is there or not, so based on requirement only, these new technologies are coming.
Absolutely, absolutely. Thank you, sir. Thank you very much.
Thank you.
Sir, namaskar, sir.
Sir, namaste, sir.
I'm KVRS Murthy. I'm the Fellow Institution of Engineers and a scientist in CSIR retired. Sir, I have two information that is what I want to ask. Who are the best architectural engineers and structural engineers across the globe for such wonderful structures? And what is our standard, Indians engineers stance on that? And who are all the global architects and engineers?
Sir, I can tell you, Arup and engineers, the US-based engineers, and most of the engineers working there are Indians actually, US-based. So, in fact, they are some of them are really very good engineers, and these things have come out of intuition. Most of you feel it, and in fact, I discussed with some of the architects who came to that national conference. They said they are learning from nature, because nature teaches us many things. Nature is inspirer. In fact, I did some work on nature-inspired buildings. And I think Anchuri is here. Anchuri?
Sir, I am here.
I think you can add something in how this thing.
Yeah. In fact, sir, as sir said, the optimization comes to the shape, and then the reduction of strain energy and all. And the need of the hour is not only the the regular form, but the excited shape, and the world is going beyond aesthetics and all of the things. We need iconic structures. So it's not only requirement of but say Burj Khalifa. You can see, the world is looking towards Dubai because of the Burj Khalifa. So the need is there, and then shape optimization can be done by learning the things from the nature, like from the nests and all, as sir said. So aerodynamic things and biomimic things are important, and regenerative design is coming up, sir. So a lot of work is going on, and I'm fortunate to work under sir. I'm grateful to him. In fact,
Very nice, sir. Thank you, sir.
Dr. Ramanrao,
sir,
I'm not speaking about the tall buildings. Of course, Srish was asking whether there is necessity for us or not. Definitely, because in India we have got a lot of space. So we also, in future, will have to go for vertical expansion only. Horizontal expansion is not possible. So that is one thing. Also, I am very much impressed with the shapes. In fact, if you had seen in Kanha, Chegur, our ashram has built one beautiful meditation hall. I request you to kindly go and see once.
Okay, where is the location, sir?
Chegur. It can
It is near Shamshabad.
Near Shamshabad.
Okay, so I will visit, yeah.
Please, I'll also accompany you when you come.
Yeah.
Very good place. As far as meditation.
Anyway, I wanted to inform you that I just completed my turn at NIT Warangal. Now I have been again appointed as NIT Raipur director now.
Very
for
good.
another 5 years.
Congratulations, sir.
Thank you.
Congratulations, sir. Environment.
So my next assignment is at NIT Raipur for a further period of 5 years. But anyway, we are all connected, so place does not matter anywhere.
Yeah.
Sir, we are lucky because that is the only state we didn't have much contact. So at least there is our director, at least we can come anytime.
Yeah, nothing is in our hands, sir.
Sir, we will come to Raipur, sir. Sir, Dr. Ramana here, sir. We will come to Raipur.
Please do visit. Raipur is a capital city, and there is something called as Naya Raipur.
Chhattisgarh.
Yeah,
Naya Raipur is a good example of sustainable engineering.
Yeah, well town planned.
Yeah, well planned and beautiful. Please come. Be my guest. We'll be very happy, sir.
Thank you, sir. Definitely.
Raman Rao, VS Rao here. Enjoyed your
Namaste,
lecture.
sir. Bhavana, sir.
Namaste, sir. అందరూ ఈరోజు మాకు అదృష్టం కలిగింది అందరిని చూడటానికి.
మా ఇద్దరు క్లోజ్ రిలేటివ్స్ సార్ బాబురావు గారు తర్వాత బిఎస్ రావు గారు ఉన్నారు.
సుభాష్ బాబు గారు.
They are my close relatives.
Enjoyed your lecture very much. I just sat there. I didn't even move from my seat.
Thank you.
Very nice of you.
Thank you, sir. Thank you. How is your health, sir?
Maintaining.
No, that is...
At the age of 85, what else I can
so we always talk about structural health of buildings. So now
And Anchuri also, I heard him after a very long time.
Today, all day has spent for us.
VS Rao garu own driving school, sir. Own driving school, sir.
Yes, please.
Shankar Shivratri is, I think, alumni of NIT Warangal. He is also here.
Yes, sir.
He is here only. He is actually in my cabin. Actually, due to some other work, that's why I went and I brought somebody who was speaking regarding some work in the assembly hall.
So thank you very much, sir. I think we will meet again, sir.
Yeah. Nice, sir. Nice. Thank you.
Myself is also alumni of REC Warangal, sir.
Okay, sir.
And also we thank you, sir. Very short
sir,
notice also. Immediately you have given a consent to deliver.
Yes, and Raju Garante chala regards, sir. I no one let me tell you, I wanted to prepare the lecture, but the same old lecture I gave. We required some modification, but anyway, since there was no time and I was traveling.
Thank you so much, sir.
Even I heard that it went on very well. I could not fully listen your lecture, but our secretary was telling a very nice lecture it is. Thank you, sir. Thank you. Now I think all questions are over now. Shall I request our honorary secretary to go for the proposed vote of thanks?
Thank you, sir. Chairman, sir. So it is my pleasant duty to perform vote of thanks. Respected Chief Guest, Professor N.V. Raman Rao, FIE, Director, NIT Warangal, Engineer B. Brahma Reddy, FIE, Chairman, IEI Telangana State Center, Engineer G. Srish Kumar, MIE, son of late Engineer G. Prabhakar, and convener of this webinar. Past Chairman, Council members, past honorary secretaries, members of Telangana State Center Committee, corporate members of IEI, distinguished guests, family members of Engineer G. Prabhakar, past President IEI, representatives of media, ladies and gentlemen. On behalf of the Telangana State Center of IEI and on my own behalf, I convey our sincere and profound thanks to Professor Raman Rao, Director NIT Warangal, for sparing his valuable time and addressing us as a chief guest and speaker on this occasion. Thank you very much, sir. I also thank the dignitaries, council members, IEI, committee members, corporate members, family members of Engineer G. Prabhakar, and others who made it convenient to attend this event. I also thank the representatives of media. Thanks to one and all. Now I request all of you kindly stand for national anthem.
So, sir, thank you.
Thank you.
Sir, go to the stage, sir. You are in the end tomorrow morning. Yeah. Thank you. Sir,
जन गण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
जय हिंद. Sir, మీరు అన్నది మర్చిపోయారు.